Good morning, good afternoon, good evening, everyone. This is Diane Fodell. Thank you for joining the Cognitive Systems Institute Speaker Series call this week. I'm thrilled to introduce Grady Booch, who's an IBM Fellow and IBM's Chief Scientist for Watson M. Grady is currently developing a major transmedia project on computing called the Human Experience. Grady is recognized internationally for his innovative work in software architecture, software engineering, and collaborative development environments. He's devoted his life's work to improving the art and the science of software development. Grady continues his work on the Handbook of Software Architecture and was one of the original authors of the Unified Modeling Language and was an original developer and chief scientist of Rational Software Corporation before it was acquired by IBM in 2003. Grady has been deeply involved in IBM's cognitive systems strategy for Watson and for systems that extend and transcend Watson, and is currently Chief Scientist for Watson M, focused on Embodied Cognition, which he will present to us today. So thank you very much for being our presenter today, Grady, and let me turn the call over to you.
My pleasure. Several years ago, Michael Karasik and I led what we call a Global Technology Outlook study on cognitive systems, and it eventually led to the creation of the Watson Group itself. I have been deeply involved in research since that time frame, and the last 2 years found myself moving to a new space with regards to Watson, and that's what we call embodied cognition. So think of it this way. Literally take Watson and put it in the physical world, and quite literally give it eyes and ears and touch, and let it act in that world with hands and feet in the face. And I don't mean necessarily just acting in the world physically, moving things, but also acting through influence, just as I'm doing here through my tone of voice, the way I pause, and if you were to see me, you would see certain body language. That also is a means of communication. This is what we mean by embodied cognition, and it very much builds upon the ideas of Rodney Brooks, who observes that true intelligence probably cannot come to pass unless you have the intelligence embodied in the world, physically in the world, having to deal with the messiness of the real world itself. Having done that, in effect, we have taken the learning and reasoning power of Watson and are able to place it in a number of form factors. And this fundamentally changes the way we work with a system like Watson. So in the next 20 or so minutes, I'd like to explain with you what we've been doing in this space and unveil to you a project called Project Intu with an architecture called Self that we unveiled in the open source community about 3 weeks ago at the Watson Developer Conference. Now, I want to distinguish what we're doing here from the Alexas, Cortanas, Siris, and Google Homes of the world. Every one of those is, by and large, a pipeline that involves speech to text to some level of natural language classification to an action pipeline. So I might say, hey, Alexa, order me an Uber. And what happens there is we have a keyword, hey, Alexa, which wakes up the system, which is always listening, but it sort of takes action once I say that. It listens to the next bit of speech, it classifies it, and then sends that on, in Alexa's case, to a skill. Pretty straightforward and quite powerful. We see here the beginnings of conversational interfaces. Indeed, things like Watson Conversation and Watson Virtual Agent bring us to the next level where you start having dialogue. It's not just a matter of request and respond, but request, respond, have a little discussion to gather the data I need, and then finally respond. We're looking at something that goes beyond the Alexas, Siris, Cortanas, and Google's Homes of the world, and we distinguish it in these 4 ways. First, it is something that is physically in and of the world. So quite clearly, we're dealing with issues of putting Watson and its reasoning and learning powers in ways that can both sense and manipulate the world, sensing it not just through speech, but potentially through vision and potentially through a variety of devices. One of the consequences of this is that it puts us immediately on a collision course, and I mean that in the most positive ways, with the world of the Internet of Things, because this is a matter of putting cognition on the edge. Second and third, it's a matter of taking the reasoning power and the learning power of something like a Watson to that world itself. And the learning element is obviously pretty important because it's more than just learning my speech. It's more than just learning my particular intonation or my accent, but it's learning about me. What do I typically do at this time of the day? What are my common requests? What are my vocal idioms that I tend to use? So it's a learning of my interactions as well. And lastly, it's the notion of embodiment means we really embrace the notion of there being an identity. If you will, this is quite literally the idea of the system having its own theory of mind. In the earliest days of Watson, we tended to eschew the notion of Watson being a he or a she, but quite frankly, we're embracing that notion here and saying, no, there really is a he or a she or an it behind it. And having done so, this leads us to potentially some really interesting kinds of human-computer interaction. Now, having done that, oops, wrong direction, go here. Having done that, it yields a number of form factors. As we took a look at several use cases that I'll unveil in a moment, it became very clear to us that we could evolve a common architecture that would attend to many different manifestations. Our earliest work was dealing with robotics form factors, putting Watson in a robot, such as the Now or Pepper that you see on the left-hand side. In fact, you may have heard of Watson's Connie, which we placed in Hilton hotels, and that's using the form factor of the Aldebaran/SoftBank Now robot that offers the use case of a concierge. So the use case, the architecture we evolved was first off for that particular form factor. But in the last year, we have found that we're not interested, obviously, in IBM being a manufacturer of robots, but rather we've reached out to a number of robotic manufacturers and found ways to put the system we built behind every one of those. And I'm showing you some examples here. The one on the right-hand side is a particularly intriguing one. This is Sophia from David Hansen. David has built a number of hyper-realistic humanoid robots, and the system I'm about to describe to you we place behind it. But also we've done so for a variety of industrial robots as well. Another form factor is that of an avatar. You're looking here at not a picture of a baby, but rather a computer-generated baby, which is from a company called Soul Machines. Soul Machines originally was out of the University of Auckland, and they developed technology in association with John Cameron's movie, The Avatar. And what they've done is build a neural network that drives a very precise musculature of the human face. Now, they have other versions beyond just the baby. They have adult versions as well. But the remarkable thing is now you can get some incredibly realistic expressiveness with this kind of an avatar. And again, we've been driving to build a system that would allow you to couple Watson to such an expressive system. Another form factor is that of spaces. Imagine putting, the phrase we use, putting Watson in the walls. Putting Watson in the walls of a boardroom or an assisted living center or an aircraft or a spacecraft or a surgical room. So in each of these cases, I might say, for example, if I'm an assisted living center, hey, Watson, have I taken my pills today yet? And Watson might say, oh, no, you haven't. In fact, let me get them for you. And a small robotic assistant might be able to deliver it for me. Imagine being in a spacecraft, such as going to Mars. And this is the HAL scenario, albeit without the homicidal features as HAL had. But in effect, because we are going to Mars and we're some 100 times further away than we are to the moon, we can't rely upon mission control on Earth, so you have to take mission control with you in the walls of the Orion spacecraft. Putting Watson as an embodiment would be an ideal thing for that. And lastly, you can imagine this as in a device, in an object of some sort. And again, this is where it puts cognition on the edge and very much a collision course with the Internet of Things. There's been some fascinating research that we and others have been doing in the area of augmenting a chair. It appears that one can get some sense as to the progression of Parkinson's based upon the way a person raises and lowers themselves from a chair. So imagine having an instrumented chair that could assist a person as we find that disease evolving. So again, we have multiple form factors, taking an embodiment and putting it in a robot, in a space, in an avatar, and a device, and we found we can do this with a common architecture. Now, if you know my previous work, you know that I'm primarily a systems architect. Indeed, let me be very clear, I am not a cognitive scientist. I am a systems engineer. So the way we've been approaching this is to say, let us view this as a systems engineering problem that involves a lot of elements of AI, as opposed to some wicked, wet AI problem that needs to be engineered. In a way, this is exactly what Ferrucci did when he developed the first architecture for Watson itself. We had in IBM a variety of really fascinating NLC and NLP algorithms, but they didn't play well with one another. And so he evolved a system called UEMA together with an abstraction called CAS. And this forms the fundamental pipeline behind the Watson architecture for rank and retrieve. And having done so, it enables one to take a variety of AI algorithms and work them together. This is precisely what we've done in the case of Project Intu and its architecture named Self. We looked at all of these use cases and then asked the question, if we were to architect such a system, what would it look like? So in effect, think of this as an orchestration platform that takes the general Watson services of natural language processing, rank and retrieve, all of the reasoning and informational things behind it, together with elements that we have learned in the area of vision and speech so that I can bring those kinds of classifiers, other reasoning things, all together. On the top here, we have the three primary sets of use cases that we've been going to market with. The first is that of the concierge, and you saw that in the form factor of a robot, being able to answer questions that a human concierge might be able to attend to. Where's the elevator? Can you make a reservation for me for dinner tonight? I'm interested in Chinese food. Can I get extra towels for my room? And in each of these cases, it's conversational, but it's more than just Watson conversation, because here we're dealing with personalization. Here we are dealing with the ability to, and I just see that I got knocked out of the meeting, so bear with me a moment while I come back in. All right, meeting is currently recorded. Here I am. Let me share again. Let me do this, and here we are back. So in the concierge case, you can think of it as more than conversation, because here I'm dealing with personalization and also the ability to move the conversation from one place to another. The problem with conversation, as good as it is, even with chatbots, the best of them, is that you end up with a combinatorial explosion of rules that one must end up with. And so instead of building lots of deep kinds of conversational rules, let's break these apart. And so this leads us to more agent-based things. The retail use cases is kind of like concierge, except we now move in the three-dimensional world. Imagine a robot or an avatar that follows me in my phone. So as I walk through a store, it might say, "Hey, over here is an interesting item. Your son is having its birthday. They've expressed this interest. How about this? And let me pop up an offer for you as well." And as I go about the world, my vision might say, "Hey, there's a bit of trash on the floor. Let me send the message behind the scene to the janitorial staff." If you take this to the next level, it leads us to the use cases of elder care. Imagine, again, placing Watson on the walls of an assisted living center. So now I can watch over what's happening. I can learn from your common behaviors. At this time of the day, you tend to do this. You are not walking as much as you used to, so let me urge you to do that. You've fallen and you can't get up. Let me call for some help. These three sets of use cases fit very well together, and as we threw these to the system we were trying to build, we found, again, a common architecture is possible. On the bottom right-hand side, we found a number of use cases in the industrial robotics case that also applied. Imagine having a cobot for me, and I'm using here a term from Manuela Velosa, a robot that's sitting beside me uncaged, and it has to be obviously very safe because out of a cage it may have the torque that could potentially kill me, but it has to be aware of my presence. But imagine I'm now preparing a pump. It pops up for me in my augmented reality glasses, an explosion of what that pump looks like. And it might say, "Hey, you need a screwdriver for this next bit. Let me get it for you." Imagine, as you expand that use cases, all of the reasoning and conversation and perception necessary to make that happen. Take that to the next level, and you get the cooperative manufacturing, where it just not only does these things, but learns by watching you. The next level, as you see in the middle bottom, is that of a cognitive boardroom, and this is what we've done with our mergers and acquisitions work. At World of Watson, we had a long demo showing this, but it's a matter of putting Watson in the walls where I have a cognitive assistant to which I can speak and knows about me and knows the context. It has degrees of spatial intelligence as well as people intelligence. Who's in the room? Who's talking to whom? I just heard an utterance. Who said it? Because I can't tell from the voice, but I can certainly infer it by knowing where in the room that came from. Going to the next level, this leads us to a variety of transportation opportunities. Imagine putting Watson in a car, in a spacecraft, in a bus, which is what Ollie is, and having the ability to have the context of the physical space itself. So these are the use cases that drove us, and if you think about it, they really are quite complex. They require some really interesting opportunistic behavior, but as we dove into it from an engineering perspective, they had a common set of characteristics. Now, that led us to realize there were some really interesting, wicked problems that needed to be solved here. Context is perhaps the most important one. And, of course, context is essential to any degree of conversation. If I'm doing something like, hey, Watson, get me a screwdriver, you need to know the context of what am I working on, what step am I in this particular process, and based upon that, do I need a Phillips head or a flathead screwdriver, and where might that be? So context is absolutely essential to any kind of meaningful conversation. Sensory fusion is also relevant because now I might be able to fuse not just speech, but also my vision. I heard an utterance, and the cameras in the room might be able to help me identify, oh, I saw this person's lips moving, and furthermore, there was, through the 3D triangulation I could do for the voice, I could identify, oh, this came from this part of the room, therefore I have a reasonable level of confidence that it came from you versus that person. Knowledge representation is also essential. The notion of how do I represent, if I'm in a physical space, how do I know where the walls are, where the doors are, where the furniture itself is? And this is more than just social patterns of knowledge, for which there are quite a few ontologies on the web, but now it's dealing with really information in the physical space itself. This also leads us to some really interesting things we must attend to in literally theories of mind. If I'm interacting with you, I as a human have some sense as to your intonation, your emotional state, your not just your emotion, but also your personality that I can infer over time. And I begin to develop a model of what your values and your goals are. Imagine if I could do that also in an automated system so that Watson begins to build a theory of mind about you and can react in an appropriate way. But it's not just a theory of mind about you, it's also building a theory of mind about the device itself so that there is a degree of personality. I had a chance to interact with the people who developed Siri. They've gone off and left the work they did first at SRI and then Apple and formed a company called Viv, which, by the way, was just recently bought by Samsung. And they told me something very interesting. They indicated that Siri for them really took off at the point in time that Siri began to get a personality. And that is part of the idea of having a theory of mind. So how do we do this? Well, this led us to create a system called Self in a project called Intu. Here are some of its basic principles, and I think the most important one is we're not trying to build a general artificial intelligence. All I'm trying to do is to build an illusion of intelligence, and especially a system that embodies ideas I showed you in the previous two slides, but is one that learns as opposed to primarily is programmed. There are a number of significant design decisions that drove what we did, and this is actually an hour unto itself, but let me touch upon the most important ones. First, we built a hybrid architecture in which there is explicit symbolic computation in the center with neural networks on the edge. This allows us to bring the best of both worlds. The beauty of neural networks is that they can do some amazing things with regards to reasoning and perception. The downside is, unless you get to a complexity of a neural network that begins to approach the network of a human mind, or somewhere a little bit lower than that, You can't go to a neural network and say, why did you decide that thing was a cat? Or why did you make this particular move in AlphaGo? That notion of reflectiveness is very difficult to achieve with modest-sized neural networks. But we know how to do that very well with symbolic systems. On the other hand, there are certain tasks like grasping, like inserting, like picking, like perceiving that are much easier to do in neural networks. So let's build a system that brings those together. The next two design decisions bring together some classic models of cognitive systems. First, it's an agent-based system. So we've taken the ideas of Marvin Minsky's Society of Mind, who says that intelligence emerges from the behavior of a variety of small agents that work well together. And we made the design decision that they shall communicate opportunistically using blackboards. We put that together with Brooks's ideas of a subsumption architecture in which he observes that behavior happens in a hierarchy of cognition. That led us to a system called Self, and here is its architecture for it. So its major subsystems are a subsystem dealing with perception and sensors, for which there is a blackboard that captures the essential situational analysis in the moment. There is, on the right-hand side, a similar set of systems for the models that capture the models of the world, models of others, models of self. This is where the theories of mind and model representation exist as well, too. But there's also a blackboard that represents the current semantic situational awareness and a set of agents that act upon it. In the center is where we have the primary action of the system, a series of agents that work against a blackboard that define and affect what the system is thinking at the moment, that work together to carry out the behavior of the system. So this is what we've been building the last couple of years, and it exists and it's real today in a system called Project Intu. You'll see a URL here at the bottom, and you can go to it, and you can actually download and begin to use Intu today. And there's a gateway. You can start using it with some of the basic services out of Bluemix, and you can begin to put it in something as simple as the TJ bot. You can put it in your laptop. You can put it in a robot as well by going to this platform. Physically, Project Intu exists as a small kernel that lives on the robot device space avatar, and everything else is out in the cloud. And we have this running on a variety of platforms. So it works on Mac, on Linux, on Windows, and even on a Raspberry Pi. It sits on top of things such as ROS, the robot operating system, and already we put this together with a variety of robotic platforms. So go out to the URL and begin using it as well. The way you can imagine it is, and I've actually talked about this a bit, there is the physical piece that lives within the device itself, and then you can also access it via a browser that allows you to get to a gateway and bring in various agents, put them in the device itself, choose which agents, and also extend it through your own kinds of agents and plans. Now, that's what exists in the world, and here's the gateway you'll see if you go to it. But we also have behind this a pretty fat set of research activities. I play an interesting role because I'm the architect for Project Intu and the architecture itself, and so I work very closely with the Watson Group and Watson IoT and Watson Health. We're moving this to become our common platform across all of those systems. But I also lead the research effort that has about a dozen projects in 8 different laboratories around the world that are using Project Intu and bringing us new facilities and some deep research in each of these spaces. We have some projects associated with goals and planning in the area of spatial and people intelligence and assisted learning and unsupervised learning, as well as learning through sparse samples, and then also some work in the area of fusing what we're doing with the work from Dharmendra's efforts in True North. We've also divided these out across a variety of solution areas, so we're focusing on a number of form factors. And then finally, not shown here, we have collaborations with a few universities as well, and we would love to have some more that work with us that use Intu and expand it further in the space. So there you go. That is what embodied cognition is about. It takes us far beyond the Siris, Cortanas, Alexas, and Vivs of the world and takes the reasoning power of Watson in places in that world in a variety of form factors. It's real. There's some deep research behind it that continues on, and you can go access it today. Let me pause here. I've got about 4 to 5 minutes for some questions, and I'll open up the line. Operators are standing by.
Thank you, Grady. Thank you. This is very exciting. Audience, please press *1 to unmute your line to ask a question of Grady.
Hi, Grady. This is Jim. Could you elaborate a little bit on some of the elder care thoughts?
Of course. There's some really fascinating work taking in 2 places. Sam Adams, which I can point you to, is doing some work out of the East Coast, and in Japan, where you might imagine elder care is a huge effort right now. There's a tremendous work going on in conjunction with the Japan Post Office and further research beyond that to begin to instrument assisted living centers and even people's homes to provide Watson in those spaces. So this is probably a talk unto itself. You can reach out to me via email, and I'd be happy to connect you with them. But in brief, it's a matter of saying, if I have both elder care as well as health care, these are related but a little bit different kinds of things, let's see if we could bring Watson to that forefront, but also add the idea of conversational interfaces and connections with devices in the real world.
Interesting.
So that I don't know if I answered your question, because this is a big topic. I'll just say that there's a lot of cool stuff happening there, and email me and I'll tell you more about it.
Okay, thank
you. Grady, this is Marty. Can you hear me?
Hey, yes, I can.
Okay. The ethical decisions constitute, if you dig deeply, is a pretty wicked problem. How are you approaching it?
Very carefully. So Francesca Rossi, who represents IBM in our relationships with Google, Facebook, et cetera, you know of the consortium we created. About a month ago, I approached her and said, hey, Francesca, I want to challenge you. Take those ideas you've got, and I want you to turn them into code. So we're standing up a project with Francesca and Jeff Kephart to do that very kind of thing. So all I can say is stay tuned. Jeff and Francesca are leading this effort right now, and we're taking the things she knows in that ethical space and trying to turn them into code. So that's about all I can say at the moment as this effort begins to stand up. But I want to turn her ideas into real running code. If you have some ideas of how we should position this, reach out to me, because I'd love to learn your point of view.
I would like to do that. Thank you.
And I'm delighted you picked up on that, because this slide flashed by, and so I'm tickled.
No, I have a very large group of scientists that are thinking very deeply about this and are finding the more they think about it, the more complicated it gets.
It is freaking hard. I'll tell you one other use case we found this to be with. We have robots that have torque that are sufficient to rip a person's arm off, and yet use cases are driving us to have cooperative robotics where those robots are sitting outside of a cage with the human. Now, ethical issues and safety issues come to the forefront. So our question on the table for us is, how could we build a safe system so the robot has enough awareness of the context and what's going on so that it could be safe? That's not quite ethical issues, but it's issues of safety that are kind of related, and we've begun to figure out what we might do to attend to that. I'd love to chat with you about it.
I hope we can.
I can put you in touch. Thanks, Marty. We're just at the top of the hour, so I see there's a question in the chat from Scott McLeod. Grady, I'll email that to you. But I just want to thank you so much for being our presenter today. Thank the audience who asked questions. And audience, we will have one more call this year, and that's next week. And then we'll take a break for the Christmas holidays. Thank you a million, Grady, again for being our presenter, and we will see you next time.
My pleasure.
Goodbye, everybody.
Bye now.
Bye now.